Chapter 3 NanoEdge AI Studio Datalogging Basics. In the MOOC timeline, this chapter will present the main concepts of data logging in the NanoEdge AI Studio context. But note that besides some specific terminology, these concepts are machine learning ones. Regarding the general workflow of the NanoEdge AI Studio, this chapter mostly addresses the setup of the data logging environment and shortly review the import features available in the tool. The agenda is the following. First, common terminology must be defined as it is used in this training but also in the online documentation of the NanoEdge AI Studio. Based on this terminology, the formatting rules of the inputs that are expected by the NanoEdge AI Studio will be presented. The next section will mention the exceptions to these general formatting rules, depending on the project that is selected. Then the main variables of data logging will be reviewed. And in the last section, we will see the impact of these variables on the NanoEdge AI Studio workflow. Let's consider the situation where a sensor is connected to a microcontroller that has some memory attached. A sample refers to the instantaneous output of a sensor and contains as many numerical values as the sensor has axes. Let's assume that the sensor has 3 axes and thus output 3 values. These values can be either pulled by the microcontroller or pushed to it through an interrupt mechanism. So we retrieve 3 values and the MCU stores these values in the memory. A single instantaneous sensor output generally cannot characterize the behavior of a system. This is why several temporally linked samples are needed and gathered as a signal. Once a signal is complete, it can be transmitted to be stored outside of the MCU. This is the basic process of data logging. A signal or signal example or learning example that are used interchangeably thus refer to a collection of several temporally consecutive samples. The number of samples per signal is called the buffer size. Samples are temporally linked while signals are not. They are independent, and their size in terms of number of samples and duration should be suitable to represent a state of a system. In the NanoEdge AI Studio terminology, a class is a state of a system where a system can be either a single component, such as a pump, but also all the components involved in a motorized elevator door, for example. A class is a collection of signals corresponding to a given system state or to a physical phenomenon that must be monitored. So it can be regular, anomaly, in case of anomaly detection, or class 1, class 2, class 3, in case of a classification project. In order to select the right model and generate a library, the NanoEdge Studio needs a set of independent signals for each class. The number of signals per class does not need to be the same, and the NanoEdge AI Studio expects a specific formatting for this signal. In most cases, the tool expects plain text files with a single signal per line. Throughout the given NanoEdge AI Studio project, both sample frequency and buffer size are fixed, so they must be carefully selected and are the main levers of data logging. Note also that the buffer size must be a power of 2 for efficiency purpose mainly. To better understand the data format expected by the NanoEdge AI Studio, let's briefly review the possible ways of import. Each will be practically demonstrated in a specific chapter of this training. The NanoEdge Studio expects data in plain text, usually each signal separated by an ASCII code corresponding to a carriage return line feed, so a new line, and each sample separated by a delimiter that can be configured in the import window. The from serial option, or from USB option, because in fact it's connected through USB, but the signal is a serial signal, It needs a data logger application as the basic one provided in this course. The provided application collects samples from a sensor in a memory buffer of a predefined size, which is the buffer size, and then it transmits the buffer on the USART connection. And this USART transmission can then be retrieved on a PC using the ST-Link virtual COM port. The NanoEdge AI Studio embeds a serial port listener and can directly log raw signals from the running target, detecting the new line ASCII codes to parse each signal. Once the COM port and its speed are selected, then the import can start in real time and stopped on demand. Each signal is then parsed based on the chosen delimiter. The buffer size of the signal, the delimiter between samples, and the formatting of the signals line per line is handled by the data logger application on the target. It is the most convenient way to do live data logging. The second option of the NanoEdge AI Studio expects a .dat file, which can only be generated by the NanoEdge AI Studio data logger feature and is in binary format. The purpose of this import function is to allow fast prototyping, even if first the board is not available yet, or the data logging is not possible on the board yet. But still, you can experience and challenge the NanoEdge Studio tool to see if it fits your needs. So the data logger feature allows to select the sensor and their configuration on the ST eval board in a seamless way. A micro SD card is needed to store both the sensor configuration and the output of the log process. So the data logger captures the signal and creates a .dat file, which looks like this one on the screenshot, so it's a binary format. The .dat format has no buffer size information. It is set when importing the log into the tool. Here you can set the buffer size. And exactly as in the previous import feature, the signals are then formatted into the NanoEdge AI Studio. The third way to import signals is the import from file options. All signals corresponding to a given system state are collected and put in a text file, one signal per line. This import mode is meant for use cases where raw data coming out of the sensor needs to be pre-processed, for example, or to gather in the same file several loggings performed independently on several days, for example. It also gives some flexibility to the signal acquisition when the data cannot be imported to the tool directly from the field. For this import method, the same data logger as the from USB option can be used to create the text files. The log is then retrieved using any COM port terminal application such as TerraTerm or Termite and put into a text file. Each signal is composed of samples values, and values are separated by a delimiter that can be specified in the tool. Such file can then be imported in NanoEdge AI Studio. The formatting described previously addresses most use cases and must be considered as the general rules for data logging with the NanoEdge AI Studio. However, there are two exceptions to these general rules. The first exception concerns one of the project types supported by the NanoEdge AI Studio, which is called extrapolation. In this case, a signal refers to the combination of all known parameters or features associated to a target value. The target value refers to the features that the user is trying to extrapolate or predict. So the difference in formatting is that each signal buffer, so each line, must be preceded by a single numerical value representing the target to evaluate or to predict. The second exception to the general formatting rules is related to very specific sensor type that can be selected with the NanoEdge AI Studio tool for anomaly detection project. In a nutshell, this sensor requires that input file only contains one sample per line. As it only concerns a very few use cases, it is just mentioned here as a reference. For more information, please look at the documentation on the NanoEdge AI Studio on the wiki page. Let's now address the main levers of data logging, meaning the variables that have a direct impact on results that can be obtained from the NanoEdge AI Studio. The NanoEdge AI Studio does not provide data, but depends on its quality and quantity to produce the best result. The tools needs qualified data that can be raw signals or pre-treated one. The first variable of data logging is, of course, the sensor itself. By the sensor, we mean the sensor selection, the configuration, or even the positioning that must be addressed by technical experts of a given use case domain. Since a correct signal acquisition methodology can vary dramatically from one project to the other, some field expertise is needed. Let's consider two situations. For example, on a frozen system, one or several sensors are already in place on a running system. No possibility to add new ones because of the cost, maybe, or the room left on the system. And data of many kinds is available already. In this case, the goal within data logging using the levers will be to select the most relevant sensor information, as giving too much input data may be counterproductive. On the second situation, on an extensible system, where sensors can be added to monitor a pump or a motor, for example, which sensor should be used? Keep in mind that more than 80%, maybe 90% of anomaly detection is achieved efficiently with vibration or current sensing. How many sensors should be used and where to position them on the system is critical, and this cannot be answered by the NanoEdge AI Studio. This has to come from the field directly, from experts. The second important adjustment variable is the signal definition that the NanoEdge AI Studio will be given to feed the machine learning models and finally select the best one. The NanoEdge AI Studio can achieve very good results with a minimal dataset, count in hundreds. But this implies that the learning examples, the input signals, contain the relevant information on the state of the system to be monitored. There are three important parameters to consider. A signal has a buffer size, and a sampling frequency, which is the output data rate of the sensor, and consequently an associated temporal length. There is no strict rule to determine the perfect size of datasets, but the NanoEdge AI Studio solution showed in practice to be efficient from a number of signals around 20 times the number of axes of sensor. And choosing the two of these variables sets the third parameter. Which parameter makes more sense to set first depends on the use case. For example, to detect anomaly on elevator door opening-closing sequence, the temporal length may prevail. But for detecting a pump malfunction, temporal length may be less relevant than sampling frequency. To better understand these three parameters, let's consider a simple analog input and the impact of signal parameters on the actual discrete signal that will be processed by the NanoEdge AI Studio. When using a proper sampling rate, a proper signal length, and a proper buffer size, the reconstructed signal, the discrete one, will be well qualified. In fact, it represents correctly the variation of the input signal, of the analog signal. But if you use a low sampling rate with a correct signal length and thus a smaller buffer size, only 3 samples in this case, then it will lead to a reconstructed signal that will miss most of the signal variation and will not be qualified. Then, with a high sampling rate, a shorter signal length, but still a large buffer size, we have as many samples as in the first case. Then we have, let's say, a good precision on the signal, but we are still missing a lot of information. So we have an incomplete signal. And finally, with a very high sampling rate, the same good signal length and a very large buffer size, we can surely get a very well qualified signal, but we have to think also on the processing and the power consumption that will be needed to output such a signal constantly to monitor a system. Also the data transmission rate, and also there is a risk of specialization, meaning that if the signal is too well defined, it will be considered as different from a similar signal because of the precision of the acquisition. So that's something to take into account also, which is called overfitting. Let's now close this chapter on an important aspect of the NanoEdge AI Studio workflow. Even if it is presented as a linear process, in practice, the data logging variables may not be the most suitable on the first attempt. We saw that there is no strict rule to set the ideal sensor output data rate or buffer size that are drastically linked to the use case. The NanoEdge AI Studio cannot do that either. However, using it in an iterative approach, it is a powerful tool to test and converge towards the ideal data logging environment. The first step is to define a data logging environment by selecting its variable and creating an associated data logger application. The collected signals are then imported into the NanoEdge AI Studio that will test millions of combinations of signal post-processing, machine learning models, and associated hyperparameters, and produce a ranking of these combinations based on their ability to fulfill the objective. If the first data logging environment does not produce any solution with a sufficient balanced accuracy and confidence, even after several hours of processing all combinations, then the data logging environment must be tuned by adapting the variables identified previously, log new data, and iterate the process. Always try to think more like a machine than a human in this case. A human usually wants as many information as possible and will more easily filter out useless information. A machine will rather consider each and every input data as relevant, even if it leads to a too specialized model. So, in a given system where data is available from many sensors, it may be wiser to start with a limited sensor set and extend this set to improve the benchmark rather than giving all the available data to the NanoEdge AI Studio in the first place. Getting the best benchmark result is not the final target, as it concerns only a limited set of input signals. The selected library must also perform well on new signals, and the emulator feature of the NanoEdge AI Studio will help in this task. It can happen that despite some good benchmark, the selected library does not perform as expected on new input signals, maybe because of overfitting. In this case, it is needed to review which signals were used for what purpose. Maybe the real operating conditions are slightly different. Maybe some pre-processing of the signals is needed. And in the end, maybe some data logging variables need to be adapted again. Then the process can iterate again. And when both benchmark and tests provide satisfactory result, the library can be deployed. This is the end of the chapter. You may now proceed to the next one.